So next, uh, we will see that given any group, there is a space, topological space, whose fundamental, there exists a topological space whose fundamental group is that group. Right. So for that, we need to first discuss uh, some specific kind of spaces which are called cell complexes. So cell complexes are CW complexes are CW complex. CW complex. So let us see how we find it. Okay. So basically, they are subspaces of Rn. You can say that we cannot say that they are subspecies of Rn. Uh, uh, so they are identification spaces of this uh, a collection of spaces, right? So what is done actually? Uh, so basically, we will collect some building blocks, right? And then we will one by one we will assemble them, right, to get a new space. So those spaces will be called CW complexes or cell complexes. So like if I want to make a graph, so what I can do is I can just consider I can just choose vertices, right? And then because I can just if I want to have an edge, then I can just fill up this. If I want to have an edge between this and this vertex, then I can do that like this. If I want to have an edge between this and this vertex, I can do that like this. If I want to have a vertex between this and this, then I can do like this. If I want to have a edge between this and this vertex, I can, right? So similarly, similar kind of thing we will do here also, right? So so the building blocks means uh, what will be the building blocks? So building blocks will be cells, right? So a zero cell, what is a zero cell? There are points. Points are called zero cell. And then one cell. Open arcs. These will be called zero cells. So these open arcs, right? So for example, open interval you can consider, right? So these, so here endpoints will not be there, right? So they will be called, or you can consider this to be this -1, -1, something like this, right? So uh, this is in R. So this is usually homeomorphic to open arcs or one cells. And then two cells. So this is open disk, right? Open disk, three cell, open three balls, right? And similarly, n cell will be open n ball. Okay. So one cell you also can say that open one ball. Now these will be the building blocks. So we will glue these things to get a new space, and that new space will be called cell complex or CW complex. So definition, uh, uh, cell complexes, a cell complex is uh, an identification space or quotient space, identification is space of a collection of collection of cells of various dimensions obtained by following procedure. So what is the procedure? First, start with a discrete set x naught whose points are regarded as zero cells. Next, so you start with a collection of discrete points, right? So just right. So and this. Then you uh, attach one cells, right? So how you will attach one cells? So like if you take a one cell, right? So its boundary, so in one cell you will not have a boundary, but this one, the end point. So you take a one-dimensional disk, you can see, or uh, closed arc, something like this, right? And this one, this and this, you map to this x naught, right? So this may go to this one, and this may go to this one, right? So this one may go to this one may go to this one, right? Or you can just map this to both the endpoints to a single point, right? So like this. So we'll get a loop. So in general, how you are going to attach uh, n cells, it is given like this. So inductively form the n skeleton xn from xn minus 1 by attaching n cells En alpha. We will denote ion cells by this via maps phi alpha from Sn minus 1. So boundary of these n cells will be n minus 1 dimensional sphere, right? So, if you take an n ball, right, it's bound open n ball, so its boundary will be uh, n minus 1 dimensional sphere Sn minus 1. So, you map the boundary. You have a closed n ball. The boundary you map to xn minus 1. So Sn minus 1 to xn minus 1. So exactly means what is the means how this attaching is done. Uh, so this we are using these attaching maps, right? So to attach these n cells. Uh, uh, so exactly how it is done. So this means that that is xn is the quotient space or identification space of the disjoint union xn minus 1 union dn alpha uh, with a this is disjoint union this of xn minus 1 with a collection of n disks dn alpha under the identification identification uh, x identified with phi alpha x for x belonging to dn alpha boundary of dn alpha which is Sn minus 1 which is in fact equivalent to Sn minus 1. Thus I say set xn equal to xn minus 1 union alpha e alpha, where each En alpha is an open end disk or ball. Now, one can either stop this uh, inductive process and either stop this inductive process at a finite stage setting x equal to xn for some finite n, or one can continue indefinitely setting x equal to union of these actions. In the latter case, x is given the B topology. So what is that big topology? So one can continue indefinitely constructing x1, x2, x3, and so on, xn, right? And then one can define x to be union of these xn's, and one can topologize this x by big topology. So big topology is given by a set A in X is open if and only if A intersection Xn. We know means Xn has quotient topology, right? Already we know A intersection Xn is open in Xn for every n. So we will see some examples. So examples. So what a simplest example is constructing a graph. So what a graph also is a topological space. So what you can do, you can have x not, right? So that just a discrete uh, set, right? Now you want to construct x1, so you have to get x1, you need to attach one cells, right? So you consider the one closed one ball, that is the closed interval or closed arc, right? So here to attach the one cell, right? You have to map this one, right? The boundary points to x naught, right? So how can you map? You can take this point to any one of these points. Similarly, you can take this point to any one of these points. So if suppose this point goes to here, right? This goes to here, and this point suppose goes to here, right? Then you will you will have an arc something like this, right? So here, what are you doing? Here you are getting finding the identification space. So if you want to if you want to add some more arcs, right? Suppose between this and this, then again you have something like this. So initially you had these closed one balls, right? Closed intervals or closed arcs, and then these points you are trying to find out identification space, right? Uh, by identifying this uh, these boundary points with any one of these points in x naught, and then get the identification space. Similarly, you can maybe identify both the points, boundary points to a single point to get loop something like this, right? You can get something like this, also something like this, also something like this. Now, if you want to get uh, attach two cells. So what will you do? You can take a closed disk, right? So this boundary, that is this boundary circle, you have to map to this x1, right? So one day is you can map this one to this circle like this, right? So you will have, right? Or you can map everything. You can map everything to this a single point. Suppose here. So what will you get then? Then you will get a sphere here. Just see. Similarly, you can map this hole to this one, right? This hole. So this is a homomorphic to circle. So you will get this one field, right? You can map this whole boundary to a single point, maybe here. Then again you will get a sphere here. Similarly, you can keep on adding higher dimensional cells, and you will get different spaces. So, if you stop at finitely many steps, then x you can consider xn, right? Or you can continue to construct these xn's, and then in the end you take x equal to union n xn, and you give x the weak topology. So we stop here today. Uh, we'll see some more examples and then result that uh, every group is fundamental group of a space. So here we see that every group is fundamental group of a two-dimensional cell complex.